Hi, welcome to the Analog Devices workshop on the introduction to Pluto, IIO, and GNU Radio. My name is Robin Getz. I'm an engineering director at Analog Devices, responsible for a lot of ADI's open source initiatives. And with me is colleague Travis Collins.
Hey everyone, I'm Travis Collins. I'm a development engineer at ADI. I work on a lot of components like GRIO, PyADI, IIO, some support like transceivers, high-speed parts, sensors, kind of all over the map. And we've done this a workshop, a couple of years now, Robin, about now. I know we did it in person, but we're happy to have everyone virtually again. And this will be we'll be talking about Pluto itself and the infrastructure behind it. But this also applies to other devices, not only by like ADI, but also anyone that supports IIO or LibIO itself. So
we'll get into what that means as we go along too. So.
Okay. So do you want to start things off, Robin?
Yeah, sure. Let's just get to the next slide. Okay, so software-defined radio, everybody should be familiar with this. But the software-defined radio, I think, is emerging into lots of different things because more and more people are using direct RF. So when it comes out with like 12 gigasample per second converters or higher, or zero IF architectures, and we'll talk about that in a little bit as well. But almost everything from your iPhone to your drone to your Milcoms to like a variety of things is some kind of software-defined radio. So, traditional RF evaluation platforms, multiple boards, ADCs, DACs, external oscillators, a variety of different things is always super cumbersome to use. So this was back around 2010, so almost 10 years ago. This was actually state of the art at that time. And this doesn't show the 6 different power supplies, the 4 different USB applications that ran on a PC that weren't actually compatible with each other, so you couldn't actually run them on the same PC. It was never easy to replicate or use as kind of a prototyping solution. And this is why we needed a small form factor open design. So go to the next slide. And that's one of the big reasons why we designed, Pluto. Like I kind of talked about earlier, there's like superhet designs where you have multiple mixer stages, multiple amplifiers, multiple RF filters, direct RF where we have our high speed, like multiple, like 10s or 20s of RF bandwidth on your RF ADC or DAC. And then there's the second, which is zero IF, which is the architecture that most radios today use, where they will have 2 mixers. They'll run I and Q out of phase, 2 ADCs through some low pass filters. So radios from Edis work like this, radios from ADI work like this, from Lime. This is the more traditional, common kind of architecture that people are using today. But the problem is not just, even for the zero IF pieces, it's not just an ADC and a DAC. There's also calibration, filtering, correlation, correction, hopping, gain control. All of these kinds of things are very difficult to actually kind of do at a system level and get performance. This is what can actually determine the performance of your system, is all these other things, actually, not just how good the ADCs or the mixers or the LNAs are. So ADI's transceiver family would start out with the 9361. That was the one that was developed first. And then it kind of evolved past that to 9363, 9364, 9371, 75, 9009, 9002. So both in terms of higher bandwidth with like devices like the 9009, lower bandwidth like the devices like the 9002, and higher linearity. And we'll talk about that in a little bit as well, if we have some time. So this is kind of like the product table what the devices are. So it's a variety of power, bandwidth, sample rate, linearity, EVM, so and of course price point. So you need to be able to pick the radio that you're interested in based on your application. It's actually very difficult to make a general purpose radio that does that 70 megahertz to 6 gigahertz kind of tuning range or wider tuning ranges and provide optimal performance for a specific application. You'll always be able to design a lower cost or lower power bespoke radio than you will be able to do a general purpose one. And inside the Pluto SDR is that 0IF architecture. So here we actually have a block diagram of the 9361, and we'll talk a little bit about in detail what this is and how it gets exposed to IIO and GNU Radio. But it's fundamentally integrated mixer or integrated LNA, mixers, filters, ADCs, and then internal digital filters until you get to your FPGA, ARM, and your signal processing, either on your host PC over USB or Ethernet or whatever it happens to be. So inside the Pluto SDR is a small Xilinx Zinc. It's a single core 7010. And so this was actually before the single core versions were done. So this is actually a 7010-4334, which is a single core version of the Zincs. So it has a little bit larger fabric than the 7007, but it's still at that single core. So it's 28,000 logic cells, 80 DSP slices in a 13 by 13 package. And so what the Pluto does is it integrates that Zinc, the radio, some memory, some USB all together in a single design. And, so it can capture IQ with 12 bits. That's the performance that it has. Sends them to the PC for processing and is guaranteed to run from 325 to 3.8 gigahertz. But you can make a tweak to the firmware and then get it to run from 70 to 6 gig. But the performance is not guaranteed. So what it kind of looks like is this, where we have our 9363, our 7010, some DDR3, some SPI flash, that's where all the images are, the USB PHY, some power, and a few more power parts. So one of the reasons that ADI actually did this was to ensure that we had a minimum reference design so people can understand, when you bolt it all together in one platform, what could it be? What is the minimum BOM? So a lot of that was done for those kinds of pieces. It passes FCC, it passes CE, it passes FCC for compliance. It's not a type certified radio. So you won't find this on like the FCC website for type certification. It won't interfere with by itself unless you tell it to, and it'll accept interference from other devices. And so we get type certified we're compliant, similar to a telephone or like a wired telephone or VCR. It's not type certified. So we go on to the next slide.
Yeah, Robin, maybe you can comment about, like, we see a lot of copies of Pluto out in the wild, and we are actually, like, Pluto was designed to be duplicated, and we're happy that people are doing that. It's an open design. If you want to make tweaks to it or modify the design, you can take the pieces that you want. You can take the hardware design, the software design, and use those as you wish. And really, it was like one of the main goals was to show people that you could do this with the 9361 family of transceivers and a small Zinc or similar FPGA.
Yeah, so copying this is great. We absolutely encourage that, and people have done it, like Travis said. The only thing we wish people would do is wouldn't copy the name. So it just makes it confusing for people. But the block diagram of this, there's a USB PHY, there's a Zinc, there's the 9363 transceiver, there's some memory, there's some flash, there's power. And that's pretty much all there is to it. And when we look at this compared to a variety of platforms, whether that's like a system on module like Epic has, or the ADI system on modules, or even a Xilinx or Intel development board with the ADI FMC evaluation boards, it's a very similar block diagram. It's the the zinc part, like some FPGA, some ARM, some memory, some flash, some power, and some kind of connectivity. And that's basically exactly what we have on the Pluto. So we actually see a lot of commercial customers using the Pluto more for signal processing, more for streaming, more for those kinds of use cases, just trying to understand things and doing maybe some tiny pieces in the FPGA, only because the FPGA is pretty tiny. So I think like we actually have some example design showing how to do like FFTs in the FPGA to do like accelerated phosphor and those kinds of things.
Yeah, that's like a big kind of perspective that I think is really important when we're talking about Pluto. Like if you're talking about something like an FM comms with a Z board or a ZC706, or maybe even something bigger, fundamentally, like the HDL is the same, the software is the same. So moving between the two, and even if you wanted to move to a different transceiver, like the way we provide HDL, the way we provide software is through like a common mechanism. So if you want to move your design from one to the other, it's really easy to do that. And learning on Pluto is a great way to get into like the open ecosystem that we work inside. So if you learn like our GNU Radio blocks, like we'll be talking about, if you learn PyADI, the Python interface that we have, if you learn Libio and how that works, it kind of just expands to different devices, from transceivers to high-speed converters. It could be any hardware hanging off the end, like a generic like transceiver FMC card like we have on the left, or even like these more integrated solutions like these SOMs, or even stuff that ADI doesn't make, like the Epic Sidekick. We have firmware that you can use that's essentially Pluto, that you can drop on that and use that with that hardware that's not made by us.
Yeah, so like a great example is the Epic Sidekick Z2, because Epic was able to take all the HDL that we have, all the software that we have, port that very easily to their platform, then take advantage of MATLAB connectivity or Python connectivity or all the other C libraries that we provide, that we've developed for Pluto and for the development kits that we have, which like the Z board and the FM Comms 3, and immediately get all of that support on their hardware platform, including the GNU Radio connectivity.
Yeah, exactly.
So when you plug in Pluto into your device, it actually enumerates as 4 devices. One of them would be mass storage. That's where all the documentation exists. So you plug it in, you open up a drive, and there's what will be pointers to the documentation, pointers to the software, how to install device drivers. It'll show up as an Ethernet device as well for streaming data. And one of the reasons that is for is so that when you're working on some interesting kind of environment, like a guest operating system on 3 levels of hypervisors that are crazily indirected, and standard USB doesn't work. Ethernet always works on those kinds of things, because networking is one of those fundamental things you have to get working. So we want to make sure that no matter what kind of platform you were running on, it would just work. So you plug it in, it actually shows up as an IP address and a networking card, so that you can actually SSH over to it if you want. It also shows up as serial, as well as a native IIO device.
Yeah, and one other thing, so we're mentioning Ethernet is supported through RNDIS, which is it was originally developed as a tethering protocol for, I think, Android phones. Is that right, Robin? On Windows and Linux. So we also do support this kind of got released in the last firmware revision, a USB class device that will actually give you a little bit more performance, but it will only work on newer versions of Windows, certain Linux kernels, usually I think past like 4 or something.
Yeah, RNDIS was a Microsoft standard, and so Microsoft supported it, Linux supported it, but nobody from Apple was going to work on it. So Apple, there was actually a real USB device class to do these kinds of things. People finally did that. Apple supported that one, and the new version of Windows 10 supports that, and the Linux kernel supports that. And so it's a USB CDC class, I think.
Yeah, yeah. So like there was an original implementation of RNDIS called Horrendous. That worked pretty well, but I think development has kind of stopped on that, from what we can tell. And if you are on Mac, use this new USB device class, and you'll even get we see like 50% performance increase, because it's a little bit more efficient than the RNDIS implementation.
So, you know, Pluto is an embedded Linux device. It uses Linux's USB gadget framework. It actually runs Linux on the Zynq itself. So, you know, when you plug things in, you're actually attaching an embedded Linux system to your platform. It is going to show up. It can be run actually standalone. So I've actually run, you know, ADSB. I've run RTL 433. I've run the retro spectrogram directly on the Pluto. It actually attached a little LCD. It was kind of cool. You know, it does support Neon. It does have floating point. It's like a single core, 666 megahertz, kind of like Raspberry Pi 1 kind of performance. And then you can plug in USB host devices to it. So you could actually plug in USB headphones. You can plug in a USB Ethernet. You know, anything that your desktop Linux will support as a host, Pluto will also support as a host. And that's why we actually include the USB on-the-go little adapter in the Pluto box, so that you can actually plug in a thumb drive directly to the Pluto, and it'll mount the device, and it'll kind of go directly run any application you have off there. And then there's actually like an auto mounter, so where you plug in a thumb drive, and it'll start running scripts or running binaries, including multiple. So it'll start running run me 0, then run me 1, and run me 2. So if you want to play back waveforms from a USB thumb drive, you can totally do that from just from the thumb drive. You don't need anything else. Or if you want to capture data every time you push the button, so there's actually a small button that we typically use for recovery. So if you hold the button while it's being powered up, it'll go into a DFU mode. But you can repurpose that button to capture data. Yeah. To do that when it becomes capture. So it totally works in those kinds of applications. So you can connect it to a host. That actually works out of the box, Windows, Linux, Mac, embedded Linux, including like Raspberry Pi. You can plug in your favorite thumb drive, so it'll actually support that as well. You can plug in Ethernet, so you can get one of these little Ethernet dongles. The one I use is like this one is like $15 from Amazon. It actually supports Ethernet on one side and has three USB hosts on the other, and actually is has the micro USB connector on it, so it plugs right into the Pluto. And then you can actually do Wi-Fi. When you're using a Wi-Fi dongle, you know, receiving at 2.4 gig doesn't work very well. So you just have to be aware of that. But like, and all of these options are also supported in the, you know, like the default firmware. But then you could extend the firmware, because it is all open. It's all up on GitHub, where you could attach a USB speaker and actually run an FM decoder on here and make the world's most expensive, terrible sounding FM radio. And I've actually done that in the past, a long time ago. You can plug in a USB speaker, get it to play out, download or like receive FM radio stations. So there is actually a FM radio application for IIO up on GitHub as well. But so like all of these concepts that we'll be talking about for the remaining little bit will work from Pluto to a variety of different platforms that kind of scale from anywhere. Whether it's the Pluto, like the 9361, the R radio and the Intel platforms, the FM Comms 5, the dual 9361, 9371, 9375, 9009. Again, these are just increasing in bandwidth. The system on modules for the 9371 or 9361, and including the 9009 module, which actually has 2 devices, so 4 channels of synchronized 200 megahertz wide, will all work with the same tooling.
So before we move on to the next section, Robin, is there any questions in the chat? I can't really see the window.
Is it possible? Yeah, it's possible to modify the HDL design on the Pluto.
Yeah, so you can use the free version of Avado to modify the HDL reference design. I know a lot of folks do that. Like if you have access to HDL Coder, you can target it directly if you're not super familiar with Avado. So if you want to add custom IP, like filters or state machines or things like that from HDL Coder, which you might have access to from from school, something like that, you can definitely target it. But people use other tools as well, like HLS or other IP generation components to get stuff into the reference design.
And somebody actually online recently built up some Python pieces to actually take an existing firmware image, rip the firmware image apart so you can add in a few Linux applications or shell scripts that you want, and then put that firmware image back together so you don't actually have to build everything from source. You can just modify the pieces you want, which I thought was actually pretty neat. So yeah,
the firmware in general is all open. So we give you the scripts to build the whole thing. Each individual step is documented. So if you want to modify the build routes, user space, if you want to modify the kernel, if you want to modify the HDL, you can totally do that. Is there anything else in the chat, Rob?
No, that was it.
Okay. So in this next section, we'll be talking about more of the software pieces and the kind of the core infrastructure that we leverage to control the transceiver and to move data back and forth from Pluto and from the other devices that we support. You can think of this as like a driver plus a RPC style mechanism where we can run remote commands or stream data back and forth, similar to what you would do with like UHD, if you're familiar with USRP devices. So just like some motivation here, we saw this diagram of the transceiver in the last kind of section. So this is the simplified diagram of the 9361 transceiver that's in Pluto. So Pluto has a 9363, but the really only differences are the sample rate limitation and the LO limitation between the two devices. But they all have this similar sigma delta architecture where we have ADCs and then we have half bands that decimate down to grow bits. And then we feed data back to the FPGA and then back to the ARM and then over USB onto a host PC if you want to stream data off the device. And then it's just the reverse on the transmit side. So this device has a lot of functionality, a lot of flexibility, but with that comes a lot of complexity. And to control it, to do things like change sample rate, change LO on the fly, there's a lot of software, a lot of components that make this thing work. And they're in the FPGA and they're in the ARM, specifically the drivers in the kernel. And we'll be kind of talking about how these things fit together in the next few slides in the kernel and then kind of in user space and back on a host application in something like GNU Radio. So kind of I would say like the black box perspective most people have when they think about 9361 and like Pluto as a whole would be that you would have your transceiver, your FPGA in the middle, and then GNU Radio. And then there's some like magic that's happening to control the device, to push stuff through the FPGA, to move data back and forth, and then to get data back into GNU Radio. And for the next few slides, I'll just be kind of filling in the details of these individual components just to talk about how things are kind of layered, and it will help you understand if you want to do things on the ARM itself, you can do that. If you want to do things outside of GNU Radio, how you can do that. because the system's really built to be flexible, and GNU Radio is just one kind of mechanism or entry point into controlling a device like Pluto using what we call Libio, or the library for the industrial input-output framework in the kernel. So IIO is a kernel and is a framework in the Linux kernel that's designed for devices like ADCs, DACs, sensors, things like PLLs, IMUs, things that wouldn't fit into, say, like other frameworks like the input framework. The input framework is designed for like keyboard, mice, and you really wouldn't want like a DAC or ADC. Things that would show up in IIO would be like the backlight driver on your laptop, or the gyro in your laptop will actually show up as IIO devices. So if you have Linux installed directly on like a laptop, you'll sometimes see these devices show up in either in GNU Radio or through the IIO tools if you've kind of played around with them in the past. Now, IIO works on this concept of a tree structure inside the kernel. So at the top, we have this concept called a context, and a context will be specific to a board, which will have a set of drivers that are associated with it. So a context would be like Pluto would be an addressable context that you can talk to, and you'll see a number of drivers that appear, and all of those are IIO-based drivers. A context will have a backend associated with it that you can talk to it. We'll dig into the details of what a backend is, but it's essentially a way of connecting to that context, either locally on the device itself or remotely over some protocol like USB or Ethernet or PCIe or something like that. Contexts will have attributes associated with them, so they give descriptions of like, here's the firmware, here is the name of the board, here is the version of Libio. And these can all be set manually if you want to do that. There's a little INI file that you can define inside Pluto, inside other boards, that a little daemon IOD will pick up and display to just give you information about that system. Now, underneath the context, we'll have devices, and there'll be you can have as many as you want connected to a given context, and a device will be specific to a driver that is in the kernel. And a device will have attributes. It will have debug attributes. Debug attributes are things like I'd say advanced components that you normally wouldn't interact with. They might require some extra kind of configuration or extra knowledge about the device if you want to dig into the debug attributes. In the transceivers, these are like the advanced AGC settings, or there's some like loopback components that are part of the debug interface. But normally you're just playing with the attributes, and this would be like sample rates or like gain control or like LO frequency, things like that would be usually in a device attribute. And then if you dig down, each device will have two other IIO components. One would be a buffer, which will be associated with data, and this is how we move data back and forth. And this will describe like ADC information that you will get back, like codes, or data that you could send to a DAC, or like sensor data that you would get from an IMU or an accelerometer or something like that. And that will have information associated with it. And then on the channel side, this is like a bit more generic if you need to describe, like on a transceiver, you have multiple channels and they would have individual attributes that would be unique to them. Like on the 9363 transceiver, it has two channels and they can have separate gains. And you might see that in an IIO channel attribute, or RSSI might show up as a channel attribute where you want to see the received signal strength individually on each component. So IIO has this very tree-like structure, and it does that so it can generically describe different devices that we want to kind of expose. And so it doesn't try to be explicitly only for SDRs or ADCs or DACs. It tries to handle a huge collection of different components that would be usually on an embedded system. Yeah,
and I would just add to that, you know, the buffers that we have, you can think of them as traditionally as IQ samples. But as you extend your design to do more packet-based processing, those can also be, strings of, payload. So when we do a modem, there are like sometimes we will abuse IIO so that it's no longer like IQ samples, but it's actually like data payload. And so that we can still stream the data payload up with these nice tools and look at it with logic analyzers and look at with these other tooling that, we and MathWorks and GNU Radio and, use whatever tools you want to can do without having to switch totally to a new tool suite. Like the only thing you can debug this is with the Vivado ILA or something like that.
Yeah, and some things in that category would be like we have specialized IP that you could use for like a TDD state machine or frequency hopping or like loopback control if you need to do like some radar application where you need to send a buffer and then receive one and maybe do some processing on it in a loop. And you wanted to control that IP in the FPGA, you could expose that through an IIO driver. And that kind of fits, it tends to naturally fit inside the structure. And then you can leverage all the pieces that are built on top of it. So you would get access to that device in GNU Radio, in Python, in MATLAB if you wanted to do that. So everything is kind of built on top of the stack that you can just leverage if you can build something in the IIO framework. So just to talk about how you would access a driver itself. Now, this is from the perspective of being on the board that a hardware component is physically connected to, not over USB or like Ethernet, but actually made into the board. So think about you would actually be SSH'd into Pluto itself or into like a Z board or a like an Intel kit if you had one. Now, if you go into sysfs or the directory sysbus IO, you would see a number of devices and then different properties or file descriptors that would be associated with specific properties. And these are actually the different device attributes, the different channel attributes, and they'll have specific naming schemes that are associated with their channel. If they're an input-output device, if they're a device attribute, if they're a context attribute, all these components would be described in sysfs. And if you're on the device and you want to change them, you can just use something like the command line tools like cat, echo. You can open up a file descriptor in a C application if you want to do that and write things in and out. So this is the real, I would say, if you're a kernel developer, you would be very comfortable doing things this way. Or if you just want to write a little bash and you want to kind of read and write some attributes, this is an easy way to do that. One really nice thing about IIO is that it's meant to provide things in scientific units. So if we cat out, say, hardware gain, you'll see it's in dB. So things will get described as like milliamps or millivolts or lumens if you have like an optical device. So it tries to abstract things in a way that is very human readable and is not just some register dump or some really arbitrary information that you have to then decode. It tries to do that for you based on how the drivers are written.
Yeah, and so it always sort of tries to describe things in SI units or some derivative of. So like Travis said, in millivolts or milliamps or millidegrees C, because the kernel doesn't have floating point in it. So
Yeah, we'll play some tricks to get like things in floating point because there are some features in the kernel that allow you to do that. But yeah, like internally, you can't describe things that way. So they'll get exposed uniquely based on, and IIO has a kind of a definition of, or a requirement that if you're using a certain unit, it has to be of this scale. So it'll be like millivolts, milliamps, something like that. It won't be amps or volts. And that's usually because the devices that you work with are in those ranges.
Yeah, and the one that confuses everybody is temperature, because it's always in millidegrees C. And nobody uses that except the kernel.
Okay, so going back to our diagram, just filling in the first step here. So the kernel driver that controls the transceiver itself is written in the IIO framework, and that will address components through the interface core inside the FPGA fabric, and then it will also directly interface with the transceiver over SPI. So this is kind of the lowest level of how you interact with the transceiver and pull data or change something like LO or sample rate or something like that. So this is nice and all if you're a kernel developer, but when you have hundreds and hundreds of attributes, this becomes a little bit painful and especially if you need to remember, like, oh, this is voltage 0, voltage 1, in underscore out voltage filter, and then like reconstructing all these names can be a bit challenging sometimes. So as a user, you might not directly want to interface with the driver this way, but this would provide you the least kind of low-level interface that you could use to control a transceiver or any device in the IIO framework. And this is really where Libio came into play, or came into being, which is a system or user space library that allows us to abstract away a lot of the kind of low-level details or the interface to make that a little bit simpler from a user's perspective. You can think of like libALSA interfaces with audio devices that are in the ALSA or audio framework inside the kernel, and libIO is along those same lines. So it's designed to allow users easier access to control in-kernel drivers in the IIO framework. So the library itself is written in C, but we do have bindings to Python, to C#, to there's Rust ones now. MATLAB has them. So if you want to work at higher level abstractions, you can totally do that. We even have kind of even higher level Python modules like ADIIO that makes things even simpler if you don't want to go into like, I need to create this context, create this device, and then go drill into attributes, kind of extract that even higher level to make it easier to use. But the reason why it might be a little, I would say, verbose is because of its complexity or of its flexibility, because it allows you to describe all kinds of different devices. If those are ADCs, DACs, or accelerometers, or IP in the FPGA, you can do that. And IIO just allows you to do that in a consistent way. So this kind of fills in a little bit more into our system level here, where instead of directly interfacing with the sysfs to talk and control that driver, that's then in turn controlling the transceiver, we're using libIO, or this user space library, to more consistently provide us an interface into that driver and controlling that driver. And one of the other benefits of libIO is it provides a really convenient kind of error checking mechanism, so that you don't have to kind of guess or constantly look at like standard error or things like that. It is a lot more flexible or friendly in that way. So this really brings us to the backends and actually getting data off a target machine. So if from at this point, what we've kind of described, everything would still have to be done on the device. You have this more convenient library to do it with libIO, but if you wanted to, say, stream from a host PC where you had like GPUs or accelerators or a lot more processing power that you would get in an ARM, you need to be able to get data off the system first to do that. And libIO provides a way to do that through what we call backends. And backends come in a few different forms. There's a network backend that allows you to get like Ethernet off the device, 10 gig if you wanted to do that. We now support UART, so if you want to pull data off that way, you can do that. USB, as we see with Pluto, but it allows us kind of a transparent way of moving data and controlling the device from a remote context or a remote machine. So
you may think that that like serial is kind of weird, especially in the context of a software-defined radio. But you can imagine when you have a deployed communication system like a manpack, and something isn't going wrong and you want to be able to debug it, you probably don't have Ethernet on that. You don't have USB on that. You don't have any of these like attack surfaces. So what you do is you plug in JTAG. You actually emulate serial over JTAG, which most ARM systems do, and then you can talk to like all the IIO pieces, all your standard IIO pieces over your JTAG connector. And many people are using this now, and it's actually helping out lots of people, so they can go to their algorithm engineer who uses GNU Radio or uses a different high-level tool, and have their firmware, their hardware form factor, their LNAs, their entire system still talk to their high-level, their standard tools talk to their custom hardware with their custom firmware, and it's fairly powerful from that perspective.
This is a relatively new feature, so if you haven't heard of it, I think we merged it a couple weeks ago. Robin, is that true?
Yeah, something like that.
Officially, yeah, but we've been testing it for a little while. So structurally, you can think of how these backends work. Is that if we have if we take this diagram here on the right, this would be our local system where we have a device physically hooked up. So this would be like a transceiver or a DAC ADC IMU. And then on that ARM or that embedded machine, we would have libio running, and that would interface with the kernel, and then within that, the IIO device in the kernel. When you use a backend, you actually go through this little daemon that runs on the board, IIOD, and that will give you access remotely. So you have the same interface or the same library interface and the same function calls that you'd have on the embedded machine that you do on your host machine now. So instead of connecting to a local context, you would just change the context interface to be remote. It would just describe it as like you'd say IP something, and that would be the context you would connect to. If you're locally on the machine, you say local as the context description. So, and then the rest of your code is identical. So it's a really nice way to move from a host machine where you would do development. You have your big monitors, you get the system going, and then you can kind of copy that code, change one line in the context that's from remote to local, and you got it running on your ARM machine or your local, you're on your embedded target. Now, if you have Pluto or you have any ADI device that runs like Hyperlinux or any of our older SD card images, and you have libio installed, you'll see that you have this little process running here. So this is the IIOD process that is responsible for doing this translation over the network, over USB. So this is actually from Pluto. So you see it's mounted to the IIO FFS. So this is just mounting to like a serial device, and allows us access through USB to actually talk to Pluto and the drivers that are associated with it. Now, so kind of building on top of this idea, this is where GNU Radio, MATLAB, IIO Scope. We'll talk about IIO Scope in a minute. It's just a little kind of utility application that we provide. But if you want to do C++ or the Python bindings that we support or PyADI IIO, they're all just built on top of the stack. So you can run technically PyADI on the target if you wanted to do that, because it's all just using IIO under the hood, or you could run it remotely on a on a Linux machine, on a Windows machine, on a Mac if you wanted to do that. And all the applications that are controlling Pluto and talking to Pluto today are all built on this higher level stack, are all built on top of IIO and libio. So if you're using like SDR Angel, GQRX, SDR Sharp, a plethora of these waterfall tools, this is what they're doing under the hood. They're all talking IIO, and they're all just controlling the transceiver that way. And you can think of, if they can support Pluto today, it's trivial for them to kind of switch and add support for like the other SOM devices that we have, or other transceivers or other components that that have IIO drivers. So it's a nice kind of way for us to provide flexibility in terms of the architecture, so that we can kind of remove a component at the bottom, but the whole stack remains the same, and you get the same functionality because things are built to scale that way. And this really completes the whole system that we've been talking about, where we start at the transceiver and the embedded system and that kernel driver, and then we leverage libio, IIOD, and then a remote instantiation of libio to then control this whole stack through GNU Radio or through some other application that you want to use. So if you want to kind of control or do like something on the side, or use GNU Radio simultaneously with some other Python code that you can use, as long as it talks to libio, you can totally do that. And we know a lot of folks that will maybe do some DSP real time in GNU Radio, and then maybe have some side Python code or some side C application that's running that is going to monitor the device, or update something on the fly, or do that from the side. Or you bring up even like a GUI application where it's, hey, I want to do reception in GNU Radio, but I just want to use some other functionality and some other tool. Like if you wanted to use SDR Angel for receive and use that, the beautiful waterfall plots that are in that tool, but you wanted to drive a waveform from GNU Radio, you could totally do that because they all speak libio under the hood.
And the most powerful thing, in my opinion, is that when you want to change the hardware, for example, it's like, okay, you decide that 9361 doesn't have the bandwidth that you want, and you need a wider bandwidth part, you can take out the 9361, update the HDL, update the kernel driver, but the rest of the stack stays exactly the same. So you can replace the 9361 with the 9009, with 9371, with 9002, and you don't have to relearn the software paradigm. You don't have to relearn the HDL paradigm. It just kind of works out of the box.
Yeah, and it's important to note that this is not a ADI thing. It's IIO is a kernel framework, and there's drivers from TI, from Maxim. Like, we own Maxim now, but
that's not a great example anymore. So there's lots of semiconductor vendors that support IIO. Yeah. Is not an ADI thing. It's ST, it's NXP, it's TI, it's the regular people that compete on the hardware side, but then try and provide a common standard framework so that the value is actually on the hardware. It's all about the hardware performance and getting the best performance for what you need, and keeping the software environment all the same. That's the way I like to think about it as a hardware person.
Do you have any questions in the chat, Robin?
No, not yet.
Okay. So let's dig on some of the tools that come with libio. Now, you can think of these if you're coming from like a USRP style device, like UHD, like Find Radio or Find Device. I haven't used UHD in a long time, but there are similar concepts in IIO. There's a number of tools called the IIO command line tools, and you can actually apt-get install these today. If you grab the latest source, there are some newer features that you might find really useful.
So a great way to think about these kinds of things is like the Linux kernel's audio interface. So, which is the advanced Linux sound architecture. So ALSA is kind of this generic term that means different things to different people. And when we talk about IIO, we use it just as poorly as all the ALSA people do. Sometimes when we say IIO, it means the kernel side. Sometimes when we say IIO, it means the library side. And sometimes when we say IIO, it means the user space utilities side. So this slide here would cover the user space utilities. What we talked about before was kind of the kernel side and the library side, if that helps.
Yeah, so all these utilities are built on top of libio. They're not using some specialized code, anything like that. They're just generic utilities that are there to allow you to find contexts, to poke at different attributes, to pull data in a very generic way. So if you need to go in and debug something or create a bash script where I need to write a few attributes in, this is really where these tools come into play. I wouldn't really recommend using them in a bigger application, like necessarily streaming data or piping data out with like IIO read dev and write dev. People do that, but we tend to use these to just do debugging, do simple changes. You can read and write registers if you want to do that. So the first one here, yeah.
Yeah, it's for like debug, because doing things with the shell is super easy to do, but not very time efficient. So like not computationally efficient. It's time efficient from a development standpoint, but when you want to get performance, that's not what you do.
So just to like dig into these a little bit. So there are 5 main tools that come with the IIO command line tools. The first one, IIO info, is really there to help you to find contexts and to pull out, kind of do like an attribute dump of a given context. So it would, if you wanted to share, like, here's my configuration, this is a way of doing that from the command line. So typically you'd pipe this to a file, be like, here you go, here's my configuration, tell me what's wrong with the way I'm setting up the device. IIO attribute is a way of reading and writing different attributes. This will write channel attributes, debug attributes, context attributes, or no, sorry, context attributes are read only, channel attributes, and I think that buffer attributes you can read from and set. The read and write devs allow you to stream data from channels that have buffers in them. So if you want to pull IQ data out from the transceiver, you could totally do this. It's probably not the most efficient way to pull data from a device, but it's a kind of an easy way to debug, like, am I getting data? Is it all zeros? Is it, am I getting reasonable throughput from the device? And then IIO reg at the bottom is a way of actually reading and writing registers of a certain IIO device. And this comes in handy for like HDL, for 9361, for really advanced things. If you want to be able to do that, you can use IIO reg to do dumps if you want to do that. But these are really low-level tools.
It's a great way for driver developers to debug stuff if they're trying to figure out the driver is doing what they want it to do as well. So if you use like IIO attribute to write some functionality and you're trying to verify that the driver is doing what you think it is supposed to be doing, you can use IIO reg to actually look at the register inside the device across Ethernet, across SPI, across all the way, and then get that back.
Yeah, and if you come to ADI through Engineer Zone, which is our support forum, and you want to do something, let's say, very advanced with a device, like in GNU Radio, we don't necessarily provide every knob in the block masks, but if you wanted to change something simply, we would give you a command like IIO attribute something to modify like some advanced setting that's not necessarily exposed. And that would just be a really easy way to modify something on the fly. Actually, Rob, can you talk about this one a little bit?
Yeah. So
features.
So when you have Plutos plugged into your network or across USB, you want to be able to discover them. So there is a scanning feature in IIO. So to be able to do that, that's exposed in IIO info -S, or actually all the tools actually support it with either uppercase S or lowercase s. So like it'll go over Ethernet, it'll go over USB, it'll search for these things using zeroconf on Windows, Linux, Mac. And we actually use this when I have, so when I do stuff in my development on my lab, I plug stuff in, and I think I have about like 8 or 9 different IIO devices hanging out on my network. It's probably pretty atypical, but this will show you what device it is, what devices are connected, so you can make sure you attach to the right one, which is super useful when you're using DHCP and you don't know what any Ethernet address really is.
Yeah, and kind of like one of the most important things is this last piece on the kind of the scan. So this is the actual URI that you would plug into either these tools and GNU Radio into Python if you wanted to address a specific device. There are some kind of like auto discover features in the GNU Radio blocks, but that doesn't apply to every instance of them. And if you have multiple devices or multiple boards hanging out, if you had like multiple Plutos hooked up, this is how you would address them, by using these URIs here at the end. And they're unique for, you can see this one's USB. You have them for Pluto, or excuse me, for IP here. And then there'll be other ones. If you're physically on a board, you'd see it would say like local in the URI name on the end.
Well, local means you're on the local network.
Yeah.
Yeah. That's yeah.
Yeah. Yeah. So now so we talked about the libio itself and how bindings exist. So on the left here is an example of how you might use the bindings to directly control Pluto. And these can be a little cumbersome to use, to say the least, because you need to drill down and address every individual channel, pull it out, find it, go into the frequency, pull out the dictionary, pull out the value, and this can be extremely verbose. We do have a top-level Python module that you can use called PyADI-IIO, and this will have device-specific classes like this one for Pluto. We'll have one generically for 9361 for other boards that we maintain, and you'll have advanced properties that are a little bit easier to address directly. And all of these will have documentation associated with them.
Yeah, so the IIO version is a very standard Python to C type interface, and the PyADI-IIO, or what I like to pronounce that as PyOD, is a much more Pythonic interface.
Yeah, and you can actually get both of these through pip, through Conda. I know Ryan is doing a great job at maintaining those pieces. He kind of beat me to the punch on maintaining those in Conda Forge. But if you're using that today, you can just do pip install, and you can grab both the libio bindings. You can grab libio itself through Conda, through Anaconda, and you can get PyADI as well. Now, if you want to move up the stack a little bit more, and you wanted to be able to see a waveform, send a waveform in a slightly more convenient way than using the command line, we have an open source tool called IIO Scope to do that. And IIO Scope is based on a plugin architecture. So we'll have specific plugins for specific driver combinations. So when IIO Scope attaches to your system, or it connects to a context, it will look at the drivers that are associated with it and say, hey, this is a Pluto, or this is an FM comms board, or this is a 9371, and then it will bring up a certain plugin that kind of exposes different properties or different configuration of a system. And it will also have plotting capability. So here's just an example of the FFT plot, or the frequency domain plot that exists in libio. So this works on Windows, Linux, Mac. It's completely open source. So if you want to go in there and add some of your own plots, or add some of your own plugins, or additions to plots. I know Robin has recently added like additional windowing functions to plots. You can totally do that. So this is more of a, if you want to do some more debugging, but if you want to pull some data back to see if something's working, IIO Scope is the tool to really do that. And this one I think is for you, Robin, the zero conf pieces.
Yeah, so I was going to just add that IIO Scope is the visualization tool. It really doesn't have any comms processing in it. So if you want to see how IQ looks like, you can totally do that. You can look at FFTs. You really can't look at constellations or anything like that, because there's no time recovery, nothing like that.
Yeah, you can look at a constellation, but it
rotates like crazy. Yeah. So any GUI can use this is kind of what we were talking about before when he talks about the scan features. We actually have zero conf. So the pull downs that let you say what a discoverable device you can find on the network, that's actually how it's finding it, is with those scan functions. Since, you know, it has access to both the USB and IP, it'll actually go out and look for all of those as well as local devices. And, you know, it tries to do that in a self-hosted kind of environment. So you don't need Bonjour or anything like that. Also on Windows, it'll just work out of the box. And we'd like to implement those things in GNU Radio, but it's hard because of the way the masks in GNU Radio and other applications work when it comes to when you can run initialization code to populate those pull downs.
Okay, so I'm just going to go into just a little example of using IIO Scope. We'll be shooting out a link later that actually has a lab that goes through using IIO Scope, and then just to get everyone familiar with it. Since that can be pretty challenging to do with a room full of people on a virtual call, I'm just going to kind of go through some of the concepts of using IIO Scope and how you might leverage it with Pluto. So you can install it on Windows, Linux, Mac. I'm just going to be using it on Windows because that's my only real machine that runs PowerPoint. So let me pull this up here. I can click on anything. Okay, so it tends to auto load the last device that you used, but we'll just kind of back out a little bit. Now, the first thing that happens when you load IIO Scope from a fresh install is that you'll get this connections window, and this will allow you to both search for or manually plug in contexts to talk to different devices. If we go over to Discovery and you hit refresh, it will do a scan. So this is using the zero conf features that Robin was talking about. And these are actually part of the GNU Radio blocks as well. So I have like Robin does, I have a bunch of devices on my network right now. So one is actually an IMU that's hooked up to a Raspberry Pi. And you'll just see the driver name right here. But this is the kind of one that we'll use. So this is very similar to, this is a SOM, but Pluto will have the same devices. I just don't have Pluto hooked up to my machine because I'm out of USB ports for my camera and for my microphone. So we'll just kind of stick with the SOM for now. And you see that the information in regards to the board populates. So this is just a Z board essentially with the 9361 transceiver hooked up to it.
Yeah, but so what you should see when you plug in a Pluto is you should actually see two devices there, one for the IP address and one for the USB backend. So you'll actually get both, and you can it's identical from the user interaction with afterwards.
So once you get in, there'll be two main panels. One will be this configuration panel, and then the second, which I had closed before, is this capture window, and this is really for pulling data back and forth, or pulling data from the device and visualizing it. So we'll get to this in a second, but I just wanted to talk about this configuration panel for a second. Is that big enough, Robin? Can you see that? Okay.
Barely. Yep.
Barely.
It's,
I can't really.
it's not the panel that's too small; it's the text. But I think that is probably be as good as you can get.
Okay. Okay. So for 9361, 63, 64, you'll see panels that are associated with that device. As I mentioned, IIO Scope is a plugin based system, so it will populate or automatically load different panels. And this tool is really designed for debugging purposes, to get used to the device and to get at a lot of the complex features that you might want to use. So I would say the simple panel or the most used settings panel, we'll see a number of subpanels that are associated with different aspects of controlling the transceiver. And these panels are kind of set up based off of the kind of like the expected use cases of a device. They're all developed by kind of the driver designers. So you'll have to forgive their beauty.
It has very 1992 kind of GUI to it. Yeah.
Yeah.
Offends Travis's sensibility.
But it gets the job done. Thanks. It's not very flashy. So the first panel is really the global settings where we can set, we can load filters, change the enable state machine. So this is where you can select from FDD, TDD, pin control, and move through those modes. Minimize that a little bit. And then we dig down into the sections that are specific to the transmit and receive channels. So this is the secondary piece here is the receive chain, and this allows us to manually control the sample rates, the bandwidth. So this would change the front end bandwidth of the analog filter on the transceiver, the sample rates on the fly, and you'll see since the sample rates on the receive and transmit chains are linked, you'll see them update together. And we'll get like readouts of RSSI and gains as the receive signals change that we're pulling in. And then you'll see kind of similar feature set for the transmitter with just less options. You don't really have trackings on the transmit side. They're just initial calibrations that are performed. And then on the bottom, we have features that are specific to the FPGA. The reference designs for pretty much all of our devices that have transmitters will have signal generators or DDSs inside them. So we can generate single tones, we can do multiple tones, we can independently control the IQ of each tone that we're generating. So you can have up to 8 on this specific device because it has 2 complex transmit channels. But most of the time you just want to deal with 1 tone or 2 tones. It's just more convenient to deal with frequency and phase. You can also load data streams. So we can take a buffer and it will suck in like text files or mat files or other forms of data that are all described in the documentation. So if you want to load up a waveform or like a LTE waveform, something like that that you've generated, this is kind of an easy way to do that. Okay. Now, the advanced tab has a lot of features in it, so I don't really want to go into all the details. It's documented if you want to dig into like the AGC settings or TX monitor or the kind of like the built-in self-test features of the device. All of these are exposed to you, but that really digs down to the nitty-gritty of controlling the transceiver. And most people don't really have to worry about these things.
Yeah, well, just as a time check too, I think we only have about 20 minutes left. We definitely want to get into all the GR pieces too. So.
Okay. So I just wanted to show just pulling back data. So
yeah,
this is kind of really what the capture plot does, and you can do the same thing in the frequency domain, or just pull some signals back. Okay, so just switching back to the slides.
Make sure you close that so the GNU Radio works.
The GNU Radio section. Yeah, we're closed. We're closed. Are you seeing the right screen, Robin?
Yeah, I'm seeing it. Thanks.
Yep. Okay. So this really brings us to GRIO, which is the out-of-tree module, and now actually in-tree module that supports IO devices directly in GNU Radio. So if you want to install the out-of-tree module today, you can grab that at the GitHub link here, Analog Devices GRIO, and it's kind of the similar concept of other out-of-tree modules. You just CMake, make, install. Now, if you are running from the master repository of GNU Radio, you'll get this installed as long as you have the supporting libraries. If you have libio installed. You'll get the Pluto blocks if you have lib89361 installed as well. So this is kind of we're super excited about this now that this is integrated as part of the master tree, and should make it a lot easier for everyone to consume the IIO blocks and to use devices like Pluto. We do have a Windows build, but this is on 3.7 still, and since we've kind of integrated, we'll be likely dropping support for that binary in the future.
And Travis, there are some namespacing issues with the with master too, aren't there? If you have too many things installed in all the same places.
Yeah, so that is a common question that we get. So if you're using 3.8, you do for the Python bindings in GNU Radio will be import IO, which is the same name that the Python bindings for the library itself has. So GRIO does import IO. The Python bindings for libio, which are pylibio, will be import IO. So I know that was a bit of a mouthful, but that means if you forgot to install libio and then you installed GNU Radio with the IIO Tree module and then you install libio, it's going to overwrite that namespace. So you want to make sure you're not using the bindings if you're using 3.8 for now. Now, when you move to the master code that's in GNU Radio now, the namespaces change from import GNU Radio.io, so that kind of problem fully goes away. So just so everyone's aware of that. But if you do have a question, please shoot us a message on our support forums, and we'd be glad to show you a workaround for that. Okay, now the IIO Tree module itself has a little bit more blocks than are provided directly in GNU Radio today. This is because we actually support some other features that are in some other tools that we have. But at the low level, we have the my pointer here. We have the device sync and source blocks. So these are really where you can use any IIO device that you want that has buffer channels that you can stream data into. So even if you had like a backlit keyboard that had a buffer channel, you could use these devices to stream data into your flow graphs. The top level ones, or we might refer to as the top level components, like the FM comms or the Pluto blocks, are just built on top of these ones. So they actually inherit from them in C or C++, and they'll just kind of leverage or add additional functionality that makes them easier to use. Then on the attribute side, when we're not just talking about streaming data, we have these attribute source and sync blocks that are responsible for directly accessing or reading or writing different attributes from the flow graph. So if you just want to kind of update something that's not necessarily in the mask here, so if you had some strange like AGC setting that you wanted to use, that would these IIO attribute sync and source blocks would allow you to do that. So as I mentioned, things kind of inherit internally. So at the core is the IIO sync or source blocks. Then you'll have well, like how the Pluto blocks are structured is you have the FM comms blocks, and then the Pluto SDR blocks kind of inherit from that chain, because Pluto is really just a subset of the FMC style card that we offer for 9361. It just has, I would say, some additional components, like it has USB support. But if you wanted to add your own custom block that will leverage libio, a common way to do that is just to inherit from the IIO device source or device sync blocks and add some customization that would be like custom attributes or other logic that you wanted to add in your for your own device. So actually, Robin, how are we doing on time? We got like 15 minutes?
Yeah, 15 minutes.
Okay. Now, I'll just go through the masks quickly so people understand how they work. These really map to the components that we've been talking about so far in terms of IIO itself. So the context, this is the same context that we've talked about when we're addressing things like remotely or locally on a host. So you would fill in something like IP dot colon 192.168, like we saw when we were scanning for addresses, or you'd put like USB colon and the root hub and so on and so forth in your device. Now you can duplicate these across blocks within the same flow graph. So if you had a source and sync block that shared the same URI internally, they would actually just use the same reference to use the same context. So you're not duplicating context constantly in the flow graph. LO is shared between sync and source. And this is just changing the frequency that the mixers are running at. If you run that kind of extended hack that Robin talked about at the beginning, you can go from extend the range from 300 megahertz at the lower end to 70, and then the upper end from 3 gig to 6 gig. Sample rate, this is actually the sample rate at the interface. It's not actually the sample rate of the converters. They're actually running at a much, much higher rate, something at an order of like 600 megahertz in certain cases. And what's really unique about this is that it will be also dependent on the filters that you have loaded into the part. So these two filter settings are very, very important when we're talking about sample rate. So just to go to them next, logically, inside the transceiver, you need to decimate to get to certain rates, and this is really where these filters come into play. If you want to load a custom one, you can totally do that. There are filter tools that we provide to allow you to generate them, or you can just load an off-the-shelf filter that should be generally good across the board for a lot of use cases. And this will allow you to get to rates below like around 2 megahertz. So if you need to go below 2 megahertz, you need to turn on a filter or load one into the device. RF bandwidth is just the analog filter bandwidth of the front-end filters. Buffer size, this is just the data blocks that we pull back from the transceiver. And for you can increase this, and it will be actually much more efficient pulling data off, but it'll increase the latency of the data that you see. And then GNU Radio internal would kind of like break that up for your downstream blocks. Cyclic is a feature that allows you to repeat data on the transmit side. So it will take the first buffer that you pass to the block and simply repeat that in hardware. And this is a really useful tool when you're doing debugging, or if you just have the same waveform that you want to send over and over and over. So you're not kind of requiring extra bandwidth on the transmit side to just send repeated data, and the hardware just does it for you. And then attenuation is just the gain control on the transmit side. So the final pieces that are different on the receiver are specific to the calibrations. These are generally used if you are using IQ signals, if you're using quadrature signals. If you are using just single sideband, you only care about the real or the real only or the imaginary portion only, I would recommend actually turning quadrature tracking off, because this will actually make your signal easier to receive. And then the DC corrections are just essentially filters that get introduced into the receive chain to remove any DC components that are natural for 0IF transceivers. Okay, so now we just want to like be able to connect things from the IIO tools to the blocks themselves. So this is when we wanted to use a generic block. So if we didn't necessarily have a specific block for some hardware that you had, this is a way that you could do it by using the IIO tools to do some discovery, pull in some information that you'd want. So here we're just doing it for 61, but you could do this for like an IMU that you had if you needed to pull some data in from that. This is kind of the process that you would use to build up a signal chain or a block to generically address that. So if we use the IIO attribute tool to just list the devices, which we can do with this -d flag, it will give us what is available in that context. And we'll see devices that are associated with, so the phi is the device that's associated with kind of the top level configuration of the transceiver. The DDS core is the transmit half, and this will include the DDS or signal generation features if we want to leverage them. And then this LPC only device is really for the receive end. And this will have buffers associated with it. So you have to know a little bit about the device or the driver that you want to interface with, but usually it's pretty easy to pull in information depending on its complexity. So like IMUs, they don't really have a ton of attributes. If ADCs only really don't have a ton of attributes. Transceivers, they just do because there's so much complexity inside them. But usually translating or pulling this information from the IIO tools is pretty straightforward to do. So how we take this information and then we need to plug it into the generic block to allow us to address the context and then pull data. And this works by, again, defining that context, defining what the device name. So this is where the buffers are, and then the file name, which is where the attributes that we want to update on. So these can technically be the same. They don't have to be different at all, and they will be the same for a lot of boards. Channels. So these will be specific to the buffer channels that you want to pull out, and they'll have generic names usually like this. That's like voltage 1, voltage 0, voltage 0 Q, voltage 0 I, something like that on the device that you have. And then buffer is the same as before. Decimation, if you want to pull out some data in line to just do some initial like reduction in data speed. I'd recommend not using this because you'll alias. And the last section is parameters. So if you want to write anything on the fly or do anything at initialization, you could do that through this parameter set here and change like the bandwidth or change some other attribute through the generic block itself. Okay, and the kind of one of the last blocks, I think we have 2 blocks to look at, but we'll just kind of rip through these quickly. So we talked about the device source block, which is really for streaming data. But if you want to access an attribute specifically, so if there's something on the block mask of Pluto that, or something missing from the block mask of Pluto, this is a way for you to do that. So it accepts messages, and they're in the form of these the polymorphic type dictionaries. So you just provide the attribute name, the value, and then you send it as a message, and it will write that to the device. And this has a pretty straightforward interface. You just describe the URI, the device, and then you would tell it if it's a channel, a device, or a debug attribute. If it's an input or output, and this would be only specific to channel, and then it would just show up as an input-only sync device. And then on the receive side, yep.
I was going to say, and this is you might read things like RSSI, which are outside of the channel, but are exposed to just a normal attribute.
Yeah, and those things, would not be in the standard Pluto blocks, just because
it doesn't make sense.
There's hundreds of attributes, so we just want to make that a little bit easier to use. So if you want to read something like RSSI or some really strange property like AGC LMT overload high threshold, this is some advanced setting that you would have on the transceiver if you wanted to read this out into your flow graph and then make some decision or just understand what that property is doing. Usually we do this with like our RSSI, as Robin mentioned. You would just translate this call into the block mask for the attribute source. You plug in the device name, which we have here. We say it's a debug attribute, which is this $D flag, and then we fill in the attribute name. And then we just give some description of, hey, this should be exported as a double or a long or some other type, and how often to read from that attribute. So this is a really handy way to just pull in things that are not necessarily described in the block masks, or either just there's no block that exists for that style of device. Okay, so I know we ripped through that section a bit, but so if you are looking for more information about GRIO, Pluto itself, the drivers, how they function, there's a lot of information on our wiki, but it's not you might be looking for some support additional on top of that. So please reach out on Engineer Zone, which is easy.analog.com, which is where myself, Robin, other people on the team, those who have written drivers for like Pluto or other devices, or written like even the HDL, the guys that write the components are there to help you use them and develop with them as you want. Anything to add, Rob?
No, did you have 310 installed on your Windows machine, or have a build for it, or not yet?
So on Windows, so
Probably not.
So I have it running through WSL.
Yeah, okay. At least you can show people kind of what it looks like. Yeah,
I think I haven't tried Ryan's version, but yeah. So I can show you guys what this is like to use like the IIO blocks. So I'm just running. I actually pulled master I think this morning, and I built this up. So we'll just go over and look at the library here, and you'll see industrial IIO, and you'll see two specific categories. So if you have Pluto, you'll just go into these blocks, and you can pull out the source and sync blocks for Pluto. But if you have the generic ones, you would just simply use these guys to pull out different components for addressing other devices that are might necessarily be captured by Pluto itself. So this should work. So what I'm actually going to do is I'm actually going to use the Pluto block to actually talk to that other device that I have on the network. That's actually a 61. So so I'm just going to scan on my network like we showed before, or Robin showed before with the IIO info tools. And we see that we have two specific devices. One is that IMU, and then one is that 9361 base transceiver. And I have this IP that I want that we can just plug in here. So take that IP, analog.local. Then we'll look at the instrumentation, QT, and frequency of my block. And change the sample rate to something in the realm, so like 600K. And I'll hit run and just stream some data back. And the plot is somewhere on my machine. All right, here we go. We're just pulling it back some data as you normally would from kind of any device sync that you would expect in GNU Radio. But since like the unique thing here is that I'm not necessarily connected to Pluto, but it's since the Pluto blocks are built on that structure of the device source and the FM comms and then Pluto at the end. As long as your device actually has the same driver names as Pluto uses, you can actually use the Pluto block, and you'll get the same knobs and the same control as you would. So it just really kind of shows that like that flexibility of IIO. And as long as the drivers have the same names, the attributes have the same names, you can just kind of leverage the existing infrastructure to talk to the different hardware components. Okay. So I know we're really buttoned up on time here. I think it was 2:30 was the hard deadline. Was there any questions in chat, Rob, that we had?
Some people are just typing stuff. But I appreciate everybody's time. I'll probably, can you sample at the highest sample rate?
Yeah, so
yes and no. You can definitely sample at the highest sample rate. You can't stream at the highest sample rate, if that makes sense. So,
like
go ahead, Travis.
Yeah, so the transceiver itself is capable of 61.44 megasamples a second per channel, and that exceeds gigabit Ethernet. So like this, or like obviously USB 2, which is a lot lower. So if you're exceeding like the transport layer, if you're exceeding that protocol, like USB or Ethernet, you'll get these overflows you see here. But what happens is that you'll get essentially a block of data, and it will shoot that over. And within that block of data, you're contiguous, but not kind of between blocks. So you'll get a block, then you'll drop some data on the floor. You'll get a block, drops data on the floor, and so on and so forth. Anything to add there, Robin?
Yeah, no. So it's in the block, there will be contiguous data. In between blocks, assuming that you can keep up with on USB or whatever the back end is, you can keep up to whatever sample rate that is. But as soon as you exceed that, the transport scheme back end, then you'll lose samples, but between blocks, not inside a block.
Yeah, in the latest support in GRIO does do the notifications that you would kind of expect from other devices like UHD-based devices. So you'll have O's for overflow, and then U's will show up on the transmit side for underflow.
But with that, I'll definitely stop the recording. Thank everybody very much for their time. If you want to hang on and open things up for questions, we can definitely do that too. But, I appreciate everybody's time. Thanks a lot.